Meniswate Thomas Wolf. Дякую, що прийшли. Slava Ukraine. Okay, that would be all I would be able to say for today. But thanks a lot for inviting me. It was really an amazing conference. I think it was really great talk. The organization was amazing. And everybody was super friendly. A lot of interesting topics. So I'm really happy to conclude this day here with this talk on transfer learning. So I'll mostly focus on NLP, but these are really like tools we are discovering in NLP, but I think there is also a huge potential in reusing that for other type of data. It actually comes from computer vision, but like this transformer thing are like being used for many other type of data. So as Irina said, I'm Thomas Wolf. Right now I'm at Hugging Face. I lead the science team at Hugging Face. And we are a Brooklyn-based startup. And we are mostly known today for our open source work, which is one part of what we do. And another part is working on developing tools for natural language generation. OK, so, oh no, I forgot my pointer. Well, OK, it's going to work without, no problem. So here's the overview of the talk to get you all on the same page. I'll briefly talk about the concepts of transfer learning history a little bit. Then we dive deep in the anatomy of what is the state-of-the-art model today. State-of-the-art transfer learning model, of course. Then I'll talk about open source tools, what you can use to apply this tool in research and business cases. Then I talk about the current trends, and we'll end with some limits, open question. What should we do to make these models better? So actually, a lot of the slides of this talk are adapted from a tutorial on transfer learning in NLP that we gave at NACL in Minneapolis this summer with my amazing collaborators, Sebastian, Matthew, and Swaba. So if you want more details, you can check out the slides. We have like 300 slides, so a lot more than what I'm going to be able to show to you today with like hands-on code exercise and everything. So really, I encourage you to go check this thing we've made this summer. So without further introduction, let's start with concepts and history. And what is transfer learning, right? So this is the traditional way we design machine learning. When we want to tackle a task with a model, we gather one data sets on our task, and then we initialize our model from scratch with random weights, and we train our model on the task, right? Now, when you tackle another task, usually you start from scratch again. You gather another data sets, you initialize your model from scratch again, and you train it. And if you have a third task, you will do that again, right? So this is a bit strange, right? Because we humans don't do that. When we have a new task, we don't start from scratch. We like use what we've learned on all the previous tasks the thing we've learned in the school, university. And transfer learning is one idea to try to make that for models too. So we have some tasks here we call them source and target, but sometimes they are kind of close and the label can be a bit arbitrary. But we have some sort of tasks, things that we've learned a model on, and we would like to use this knowledge on a new task that interests us, so that we don't start from scratch every time. We start from something that's already quite performant on something. So why should it work? In particular for natural language processing. One reason is that many tasks share some common knowledge, right? If you know something about English, your model has learned an English task or a Ukrainian task, or if you use, oh yeah, that's great, thanks. If you have another task which is also in English or Ukrainian, you should be able to reuse some of the syntax or some of the structural similarity. So it can be syntactic, but it can also be semantic. Like you've learned a question answering model in English, you would like to be able to apply it in a Ukrainian because the semantic, the underlying meaning is the same, right? Even if the surface form is different, we know that's the same. So we should have been able to capitalize on this knowledge that we've built. The main reason is also that annotated data is rare. It's very expensive to build that set in NLP because you need to teach the people how to do this annotation, and it's really expensive. So if you can gather this data set together, it's really a lot better because your model will have more data and will be happier. And the last reason is that we have this huge corpus of unlabeled data, which is called the internet, and also books, actually, but internet is right now bigger than this. And we would like to use this, right? We have all this data that we're not really using. So transfer learning try to solve these kind of problems. And empirically, transfer learning has resulted in state-of-the-art for many, many supervised tasks right now. And I will just show you a cherry-pick example, which is this task called named entity recognition, which is really one of the core classical NLP tasks. Okay, you try to label organization or people names. And this is a task that was, this shared task was the kernel 2003, so this is like 15 years ago now. And you see there's a series of jumps. First jump in 2009, and then a series of huge jump in the last 2 years. And basically all these jumps are due to some way of doing transfer learning. So on the left, you have very classical transfer learning with a variant of brown clusters, which is really this very classical way to incorporate information from large unlabeled corpus in the world. And these were like more classical linear model. And then on the bottom, you have a pointer. Oh yeah, that's great. You see, this is the rise of neural network. Okay, this is the color bear work. And then you see recently all this is basically the combination of deep learning models, deeper and deeper, and transfer learning. And you see at the end, this is like BERT, this is the current state of the art. And Elmo is somewhere, Elmo is here. So today I'm going to talk about this part mainly, okay, what's happening right now. And you see we're still not saturating the performances. So there are many ways you can combine datasets. And we'll focus on sequential transfer learning, but just to show you, there are many ways. So for instance, you may be actually on the same task, as I was saying, like you're doing question answering, but you may have two languages, question answering in French and English. So this is called cross-lingual learning. Sometimes you have different domain. You have question answering on a news corpus, but you want to do that in your, I don't know, customer survey corpus, okay? So this is called domain adaptation. And all these have like huge history in NLP, but yeah, I won't really have time to dive on all this. And these two tasks at the bottom is when you have different tasks, and you're trying to combine them so each task helps the other. So you have multitask learning, which means that you will basically learn the two tasks at the same time. And what I talk more about today is sequential learning, in which you first learn one task and then you apply on the other. But there is a very blurry boundary here. You can basically blend these two together very easily. And so today, the topic is more sequential. So you're doing a huge step of pre-training here on a task that's not exactly the one you are interested into. And then you do another step of adaptation on your target task, okay? So this is quite all right. Word2Vec, GloVe, this is 2013. So it's like we're all in a deep learning world. So this is like 6-year-old. But this was the first time we saw really gains from splitting this process into combining two tasks together, right? Not only focusing on your target task, but also using other tasks. And this all started with verb vectors, right? So this is Word2Vec, GloVe. How do? You build these vectors for words like cats, dogs. You build them from huge unlabeled corpus. So Word2Vec and GloVe, they are actually, the corpus are really a lot bigger than the one we are using today to train BERT. So there's still a lot of room. This is like 800 gigabytes of data. And today we're training on like 40 something. So there's still a lot of room. And this was trained on a lot of data, but these vectors are only independent of the context. You will always have the same vectors each time you meet the word cat. Then after this early thing, we had a lot of work on trying to combine these vectors to build sentence and document vector, doc2vec, try to combine them by some smart averaging. And more recently, since 2018, around 2018 on Elmo, we have really the rise of word in context. And word in context, it means that if you see cats here at the end, it will be assigned a different vector than if it's cats in the middle here, okay? There's another huge trend in history behind this trend of adding more context, which is using more something called language modeling. And most of the currently successful pre-training approach are based on language modeling. So language modeling is about predicting the probability of text. So it can be here. What is the probability of this text? Usually we decompose that as the product of the probability of the words or the character or some subwords, but it's basically this kind of thing. Or it can be a conditional probability of text. For instance, in translation, you will model the probability of having a Ukrainian sentence given another like French sentence here. Okay, this is all variant of language modeling. And it has many advantages. The main one is that we don't have to annotate this, right? This is like what we call self-supervised. You use your data as your annotation. Okay? So this is really the amazing part about language modeling. Many languages today, as I was saying, have just a lot of text accessible on the internet. You have huge corpus, even for English, obviously, is the biggest one, but a lot of languages have really enough to train high-capacity model. And it's very versatile, because you can decompose this thing in various ways. You can decompose it as the probability of a word given the other, like with the chain rule. You can decompose this as the probability of a span given another, probability of a sentence given, next sentence given the previous one. These are all ways to rewrite this probability with the chain rule as different products. And so it's very flexible way to write this. Yeah, you see autoregressive, masked language modeling. This is the language modeling you use in BERT with bidirectional context. Span prediction is the current span BERT, where you try to predict several words given the other one. It's a harder task, right? And cross-view training, skip sort are all variants of this. Language modeling, the cool stuff is that it's very difficult, even for human. But you can also make small steps, like you can get progressive improvement on language modeling. And so if you want to predict, here is an example. This is BERT, the Google AI model. Here we have a sentence that says, I think this is the beginning of a beautiful, so this is from the Casablanca movie. And this is all the prediction that BERT think are the most probable completion, most probable completion. So it can be day, life, future, story, and you see they all kind of make sense of a beautiful day, a beautiful world. Well, a beautiful world is a little bit strange, but why not? Beautiful year. And so basically the model has learned to kind of compress the context in a vectors that would generalize with all these probabilities. And to do this, the model is kind of forced to learn a lot of things that will be helpful for pretty much every target task in NLP. So syntax, it has to learn that after, I don't know, like a verb, you likely don't have another verb, or you will have a noun. Semantics, this is often called a fact about the world. This is called common sense knowledge. It will learn that beautiful is associated with this kind of thing, and I don't know, like beautiful death is a rarer thing that you would make as a completion of a beginning. Okay, and basically, given enough data and compute, you can do a good job. Here, BERT is doing a pretty good job, right? And it's still difficult, so which means we haven't solved this task. So the model are basically not really overfitting on the task here. So let's look a little bit at these big models who do a reasonable job. So now I switch to the anatomy of a transfer learning model. So there are two main things that are important. There is the model and the training, okay? The model usually has two steps, because we're in this sequential training. I put the image again here. We're in this sequential training setting. So usually we have an architecture for the model during pre-training, and then we can adapt it for the target task, okay? So we have two ways we can vary the model. Currently, the main models that are used are transformers, which are this non-sequential model, which there is one competitor, which is a ULM-fit, which is a smaller model, sequential model, which is pretty good for, in particular, multilingual thing and text classification. There is, it's kind of unclear, actually, if you have to make smarter architecture. So there was a boom. There was a lot of PR around this model called XLNet, which had a smarter way to do autoregressive modeling. And actually, it ended up that just putting more data in the basic architecture outperform this. So currently, it seems like we're in the bittersweet step, which is just put more data and take the simplest model you can have, and you get the best results. So there is as a consequence, there is this trend toward more data and more models. with XLM is a multi-language model from Facebook. It's a great model. GPT-2 made the news at the earlier this year. And Megatron was the production from NVIDIA. And this is 8.5 billion parameters. So there's obviously a little problem, which is that this doesn't fit on a GPU, right? So it's not production ready yet, I would say. But still, it's quite interesting. And the most interesting part for me is that what I'm going to talk later is that you can distill this model in smaller ones. So it's still interesting, I think, to follow this trend. Now regarding training, you have the same. You have this pre-training training, and this adaptation training. You have two training phases here, okay? And the main thing that actually kind of bootstrapped the field was to start to use long-term dependency. So now, instead of training on very small example, we train them on long stream of continuous text. It can be full books, full Wikipedia pages, and the model learn like this very long dependency, and they're useful in particular to grab semantics behind just syntax. Here also during training, there is a huge trend toward using more data in both phases. So you use the as much data as you can during the pre-training, and also as much data as you can during the adaptation. So here, Brandon make a cool speech about that, taking care of your data, having more data. So this is something that's very important for us. And the quality of the data is also very important. So let's give a look how it looks. So it's a three-step process when you want to use this model. The first step is you have this sentence, Tim Hansen was a puppeteer. First step is that you're going to tokenize it in tokens. So these models, they are made to be applied in the wild. So you don't want to have a closed vocabulary, you have open vocabulary. So it can be character, but it can usually character is quite a small vocabulary, which means the model has to learn a lot. But what we do today is subwords. So when you have a complex word like puppeteer, we'll split it into puppet and and the double slash here means that this is the end of the word. This is fixed, okay? Once you have these tokens, you convert them in vocabulary indices, and then you apply your pre-trained model. So all the models currently work like this. They take this sequence of indices, and they output sequence of vectors, which are hidden states associated to each token. And then on top of this matrix, you add a classifier model, which this one is trained on your specific task. So here, for instance, is the task of saying if this is right or wrong. And so the classifier model will take these hidden states and output like 2. So this classifier model can be more or less complex. It can go for a simple linear model to a full LSTM with bells or other transformers, but the idea is that this one is adapted on your task in particular. Well, this can also be adapted, but this one is really trained from scratch on your task usually. So this is obviously the big part here, pre-trained model, in terms of compute in particular. And there's been a clear trend from shallow to deeper. So this was the earliest work on like language modeling by Bengio et al. In 2003, 1 layer. And now we have 24 layers, but we have 40 for GPT-2, and sky is the limit, basically, here. A good example right now is BERT, which is kind of the canonical large-scale pre-trained model. It has a few hundred million parameters, 24 layers, and the adaptation head is very simple. So basically, this model outputs vectors, and you just put a linear projection on top of it, and this is your target, this is your adaptation. For example, for squad, you have 3 linear layers, and each linear layer is applied on the vector, and will predict if the corresponding token is the start or the end of an answer. So it's really that simple, which is really impressive. Let's talk a little bit about the meat here, if you're not familiar with LSTM, with transformers, sorry. All these models, they're really looking the same. It's a bunch of attention layer. So first you have embeddings, so you will take these indices of the tokens that I was showing. You convert them in vectors with this dictionary here. This converts each token in vectors. And then you put them in a series of blocks which are all the same. We'll have a normalization. Attention will basically mix the vectors together, so they pay attention to each of their neighbors. We have some regularizer, and then we have a nonlinearity here, which is just a double linear layer with an activation, like nonlinear activation. It's actually a very, very simple model, I think, and when you look at it in the code, it's a lot simpler to understand than an LSTM. And the main difference between all these major big pre-trained model is how they are trained, like just the objective at the end. So GPT is trained with causal language modeling, which means that you train to predict the next token given the previous one. And BERT and Roberta and BERT and Roberta are trained using masked language modeling, which means in a sentence you mask a word and the model will try to guess the right word. Now, when you want to adapt for the target task, there is usually two steps, I mean. The first step is to remove your pre-training head. For instance, if you were doing language modeling at the end, you were projecting your hidden states to your vocabulary. You remove this linear part. And then you add the head that you have. So it can be, as I said, a very simple linear layer, which is what is mostly used typically right now, or it can be more complex and even go to a full model here. So usually when you have a more complex model on top, you probably will freeze the bottom, so you don't have too many parameters to train. So this is a simple case where your task can be, where you can keep most of the architecture of your model. There are more complex tasks. For instance, if you are training on single input sequence, which is the case usually, you train a model by predicting the web, basically, and your target task is like translation. Translation, suddenly you have two inputs. You have the inputs in French and in English, for instance. So here you have to find a way to initialize as much as you can from your pre-trained model, but you will do stronger architectural changes. One way, for instance, for these tasks, which are usually called sec-to-sec, even that usually we don't use really sequential model, but they are traditionally called sec-to-sec, is that you can initialize both the encoder and the decoder with your pre-trained model, and it worked pretty well. So yeah, this is a good example, is LAMP-LANCONO, which use that on unsupervised machine translation. We also use that in our work for like language generation, like in dialogue, for instance. How you do that? This is an example in PyTorch. It's really, really easy to write. You keep your transformer. This is the full pre-trained architecture here. And you just replace the head with your head. So this will be typically this classification head I was talking about, which is this linear layer that converts the embedding dimension to the number of class. And in this case, usually we take the first token, the hidden state of just the first token, but you have various ways to do that. You can combine all the hidden state at the end in one output, or you can do various ways to do that. And then here, so you will have two kind of initialization. So the newly added weights will be randomly initialized for your task, and the previous weights will be loaded from your pre-training model. And when you train that, so this is one example where we apply. So this was from the tutorial. So during the tutorial, we had time to do this in live, actually. And you can fine-tune it on Trek, which is a classification task, which is kind of intent classification. And the cool thing, so first you see that we reached the error rate 3.6, which is actually the state of the art, very easily. And the nice thing is that we only train for 3 epochs on our datasets, and it goes very quickly. After just 1 epoch, we're already down to an error rate of 9.1, so it's more than 90% accuracy. So these models, when you fine-tune them, it goes really quickly. After 1 epoch, they're already pretty good usually when they work. Okay, and they're pretty robust too. Like the fine-tuning step is really pretty robust. You don't really have to tweak the hyperparameter very complexly, very softly. So when I say robust, I need to add a little remark on that. Usually it's like a kind of on-off behavior. What we see is that either they work or they don't work, you see. And this is just here, that was a nice paper by by Jason from NYU, and they trained this model on, this is all the glue task, and these are just various random seed, right? And you see for some of them, it works well, and just if it doesn't work, it just doesn't work at all. So it's on-off. So yeah, they're robust because when you have the right thing, it works well, but if you have the wrong thing, it just doesn't work. So this thing is still not really clearly understood. One of the reasons in my mind is that this model have a lot of capacity. There's just very big model, so sometimes they just you have too many parameters and you can overfit something on your training set. Now, how to use these models? So I'll talk a little bit about open source tools because these are really the meat of what I've been doing, at least during this summer. One note is that pre-training this model is super costly. right? So if you pre-train models, if you pre-train a particular model in Russian or Ukrainian, you should share them because there are not enough of pre-trained models. And basically, all the compute that people spend on this, I think it's really important to share it because environmentally, we now know that training this model is kind of has some impact, some non-negligible impact in terms of CO2 production, power consumption, and so really it's important to share them. You can open PR on our repo. We'll be really happy to host them if you can't. And there are many ways you can access them and share them. The hubs are one thing. There are now 2 hubs, TensorFlow-Hub and PyTorch hubs, depending on your favorite framework. Usually the auto-release checkpoints, like BERT, GPT, checkpoints on the GitHub repository. And there are also third-party library, which will help you to access them, like NLP, fast.ai, and our own library at Hugging Face. I mean, there are various interests and advantages and drawbacks. Hubs and library, they are very simple to use, but sometimes can be difficult to modify the model. Like on a TensorFlow-Hub, you just have this black box model. So either you're happy with it, or if you're not happy with it, it's your problem, right? Auto-release checkpoints, they're usually very flexible. They're just a bunch of NumPy array, but they can be difficult to access and to use. We try to strike a middle ground with our library. Just talking a little bit about the hub. So TensorFlow-Hub is like this library for sharing self-contained piece of TensorFlow graph. So I say this is really the TensorFlow graph, like the thing that's hidden behind your Python interface. And you can download them, cache them. It's very easy to use. And each time you run the model, is basically add the right operation to your graph. So that's how it works. PyTorch took an approach that's kind of similar, but it's based on GitHub repository, which I think it's an interesting idea. So to share it, you just add a little script to your GitHub repository, and people can basically use torch.load to access your GitHub and download the model. The main limitation, as I said, of this hub is that usually you download the model, but you don't have access to the source code. Okay. At least in your own code, you can then modify it, but usually you need to clone the original author-released thing. And sometimes you want to adapt it. For instance, one thing is called adapters. So my talk is too short to talk a lot about this, but adapters are little pieces of little modules, which are usually just 2 linear layers with a nonlinearity that put inside your model. You like stuck it inside, and you just train these little pieces. They are usually very light. And you can get very good performance, like adapting your model with just training these little pieces. Usually they're like 5–10% of the total budget, so you can make your fine-tuning a lot faster. But if you want to do these kind of smart ways to adapt, you need access to the code. So we have our own library, which is called PyTorch Transformers. We made it so people can easily access this model. So originally it was BERT, but now it's got like this huge amount. And it was designed with 2 strong principles in mind. The first is that it should be as easy to use as possible and as fast to onboard people. So it's really opinionated library. Every time somebody make a PR to add an abstraction, I say no, and I close the PR. Because we really want this to be very simple. So you just know that there are 3 types of classes, 3 classes: models, tokenizer, and configuration. Actually, usually you don't even have to use the configuration, so you just use these 2 classes, which are the step that I showed you earlier, these 2 steps. And we have a common from pretrained method. We'll just take care of downloading, caching, loading these classes when you want. So really in 2 lines, usually you can load your model. If you want to build upon the library, well, you just use regular PyTorch. It's well designed. You have all the models. The model that we have are regular PyTorch models, so they are easy to integrate. And the other strong goal was to provide state-of-the-art models. So every time we try to reproduce at least one example, one official example, one official result from the author. And we also try to stay really close to the original code so you can trust the library. So right now we have 8 models: BERT, GPT, GPT-2, Transformer XL, which was a predecessor of XLNet, XLM, which is a great model for multilingual. Roberta and DistillBERT is a smaller model I'll talk a little bit about later. As I say, it's really that simple to use. So this is the use case. Actually, this shows pretty much all the things you can do with the library in one page. So usually you load your tokenizer with from pretrained, you load the model with from pretrained, you tokenize your text to convert it in the indices, and you put the indices in your model. And you have the hidden state I was saying. So you can use this hidden state to put your classifier on top. You can also access internals of the models, because it's sometimes interesting to have several hidden states to output the attention. So you have a lot of access to this. And you can also speed the model with like Torch script or things. So we try to thought also about production, and we're more and more going toward making it easier to use in production. So now I'll show you how to use it. Let's talk a little bit about current trends in transfer learning. So one big trend that you can see here, this is the graph of the number of parameters of the model versus time, is that the model can tend to grow, and they can tend to grow exponentially. So we really have larger model on larger and larger data sets. I'm going to skip this slide. Yeah, just it was about to tell you how it all got started. But there is a limit to this trend, which is that now we see diminishing returns from using bigger data. So all here, you see, these are all log scale, and you see that basically these models are plateauing. And this is a graph I just told you from your presentation earlier today, which also saw this. Well, it's a log, but you see, you need actually a model that's exponentially larger to make a linear increase in performance, which means that basically all the performance are plateauing. So there is definitely a limit, and every time you want to increase by a certain amount, you need to make your model not this certain amount bigger, but like 2 times bigger, which is basically the reason we see this exponential growth. So this is the most worrisome aspect of this trend. And there is another trend, which is a trend towards smaller models, which is kind of a reaction to this crazy increase. So we published Distilled BERT earlier this month, which is like 66 million parameters. So it's like, I don't remember, but a few thousand times smaller than a Megatron LM. And it has like 95% of BERT performance. So there's a lot of fresh work on this. A lot of people submitted papers to NLP, NeurIPS on this, like making these models smaller. And the main way we are doing that is by distillation. So I just show you a little bit. So just one note on why we want to make them smaller. So we talk a lot about training costs, but as this model reached the production level, you know that actually what will matter most for the environment is basically the inference time in production, because production, there will be like 10,000 people using it in the world instead of just 1 people training it. So distilling larger model in smaller one is really a good way to make this model actually more environmentally efficient in the long term. And we can still use a lot the inductive bias learned by the large model. So our example, we were able to distill BERT in this smaller model with 95% of performance. And the way you do that is very quick. A very quick presentation is to use 2 main tricks. One is to start from high-quality weights. So we can talk about that if you want it. It's very important, which is you basically use the teacher as a very good starting point. So it's a bit like transfer learning in some way. You see, you start from a very good starting point, and then you train the student to mimic the full output distribution. So I showed you this graph earlier. You know that BERT doesn't only guess the top word here, but it has all these possible words that are plausible, right? And if you can mimic all these things, you use this bias, this generalization bias that BERT has learned. And you do that by just, instead of trying to make maximum likelihood on the golden target, you try to mix the two, you try to match the 2 distribution. So this is just a KL divergence kind of thing, where you try to minimize the 2 distribution. So you have a lot more training signal. Basically, all these are like possible gold labels, if you want to see. It's like your data set becomes 10 times bigger because you're using the prediction of the teacher model. And now I'll finish with some limits and open question of this. So the first one I've already been talking about is that these models have some shortcomings. Basically, they are unstable. That's something we don't really understand yet, how to make them more stable, where we have some idea, but still they are huge. And distillation kind of poses the question, do we really need these parameters to start from? Do we need to start from this huge model to distill them, or could we get by a shortcut to smaller model? So pruning, distillation are a way to make them less, but this is still a very open question. Can we make them like smaller? And there are shortcomings of language modeling in general as a task. Like language modeling doesn't work for all models. For instance, if you have images, well, you can do prediction images, but that's kind of different. So we need to move out from this language model somehow. We also know that language modeling kind of put a strong emphasis on syntax, like just purely surface, but the meaning is usually harder to make to have a strong signal for the meaning, for semantics. And so basically we see that pre-trained language models are bad for common sense. Well, they are better than what we had before, but they're definitely not solving common sense problem. They say things that are just plain stupid. If you ask them what's the color of a sheep, they will say this is black sheep, just because most of the time when you talk about sheep, we add the adjective black. Because that's one of the reasons we know, everybody knows sheep are white, so usually you don't say it in the text, so this model have no way to really learn that. And that's a huge problem. It's called a reporting bias, and it's a huge problem is that the obvious is usually not stated in the text, and that's the limit of these models, one of the limits. So how we can do that? One thing would be to use grounded representation, for instance, like images, video, on which you would see that sheep are white and not black. This is like complementary information. That's exactly what I was saying. Reporting bias, usually we don't write common sense because everybody knows it, so it's really hard to learn. And the possible solution that are starting to emerge is to go behind language modeling and to incorporate other source of information. There can be databases. There's this nice work called ERNI. They can be multimodal visual representation. There will be a work called video BERT, try to use also video. And and there are many others, but I didn't put all of them here. And that's the end of my talk. Thanks for listening. Yeah. That I've solved. Well, I've tackled many problems. Maybe I'll talk more about the problem I've been trying to tackle. I think the hardest and the most interesting for me is language generation. And I think it's really the future of the field. We work a lot on language understanding, but there's a problem with language understanding, mostly because usually we write it as giving multiple choice answer, right? Usually model understanding, you frame it as a classification task where the model has to check box, like in your school exam, you have to decide between 3 answers. And there is a limit because you can usually game this with that augmentation thing. And this is, each time it's a classification problem, you can game it. And language generation is something you cannot game, really, because when you generate text and it's bad, it's bad. There is no shortcuts. It's like the most difficult task, but also the task when you make improvement, they are the more significant. So yeah, that's the task we've been tackling a lot, using transfer learning for generation. And I think, yeah, we'll probably have more approach using generation also to evaluate this model.
Thank you. How would you recommend to pre-process data for models like Roberta when a lot of data is needed, but the quality of data is important too?
Sorry, can you say it again?
Yeah, sure, sorry. So how would you recommend to pre-process data for models like Roberta when a lot of data is needed, but the quality is important?
To pre-process, so for Roberta and GPT-2, I think it's one of the great improvements is that we need less and less pre-processing because these models are really trained on raw web data. So more and more you can just input your data just like the way it is with all the mistakes, all the wrong spaces, all the typo. And the model, they are basically trained on that. So Right now, we don't pre-process. Actually, what we do is usually we detokenize the data if we have some. So if the data is like artificially tokenized, for instance, with spaces and things, we just try to remove all of this and to bring back to the raw form. So that's, I think it's going to help a lot also for downstream application, because you can remove most of the pre-processing pipeline now. Models, they don't need them anymore. Yeah, it's not really an answer, but yeah, just don't pre-process.
Thank you. Can you tell a bit about other cases where transfer learning can be used except for NLP field?
Yeah, so I think it's all starting in computer vision. So computer vision, it's like the default now is to have a model that's pre-trained on ImageNet. So vision is something. Now, what I'm mostly interested in is transfer learning for multimodality, like trying to have align corpora, like align video and text, align speech and text, and try to apply transfer learning for this. But basically, every time you have an opportunity to tack into a huge unlabeled corpora, you should think that maybe a transfer learning approach is good. So for instance, reinforcement learning, sometimes, yeah, so all the speech recognition also use a lot now this kind of approach. And sometimes it's very close to other things called like meta-learning or multitask learning. All of this is basically just various phases of the same approach, which try to gather various data sets together. Yeah.
Thank you. Which challenges today stop transfer learning models from being used in production?
Well, at Hugging Face, we have them in production. So, I mean, I think the main challenge is, besides just that it's very recent, right? So if you just take some time to test them and to decide that you want to use them in production. So beside this thing, which is just natural for every new tech, I think the main problem is usually the size. And also, do you want to switch to using GPU in production, which can be a big cost. And here we're trying to make progress, well, in a Hugging Face, but also otherwise with in other places with this smaller model. So I think like a few months there would be really no reason not to use this model if they can get better performance, right? Because you still have to, as I was saying during the panel, you still always have to start with simple method. If you can just average glove embeddings and it works good enough for your sentence classification task, just use that. You don't need to use the BERT model. But more and more, they're getting really easier to use. And the fact that we don't need special preprocessing, that they're very like simple to use, actually makes them very, very well fitted for production. There is one other thing, if I can add, is like interpretability, which is a big topic right now. And this model definitely are like big black box. We just don't know what's happening inside. So in a real life application, it can be just a deal breaker. You're like, no, we can't allow having this black box decision from the model. We need to understand a little bit. And here, you just can't use this model. And I've not seen really real improvement on this side. These models are already black box, and they probably will stay black box for a long time.
Okay, thanks. And the last question from here is, how much data is needed to make a good distilled model?
How much data?
Needed to make a good distilled model.
Yeah, so it's all really, really fresh, right? I mean, the latest, the publication on this model, they're all like a few weeks to like 1 month or 1 month and a half old. So I don't think everybody has like a lot of background on this, but I think there are two ways you can do this distillation. You can either like retrain your student on the full corpus. That's what we did in our group with DistillBERT. So we took this huge corpus, Toronto Book Corpus and Wikipedia, and we just trained the student on this. And the target here, the idea is to have a student that will generalize over various tasks. You want to keep the generalization capability. And the other option is that you focus on your target task. And on your target task, you take your target data set, and here you will train your students only on this. So your students won't have this huge generalization capacity, but it will be very good on your task here. And that's another way you can also distill the thing. And what we also did actually was to do the two at the same time. So you first distill a student on your huge corpus. So you do a pre-training distillation, and then you do a fine-tuning distillation. When you distill again, your students, again, a teacher that was fine-tuned. So you can do both of them, actually. But then you need more compute, so yeah.
Okay, thanks. And I believe we can have one question from the audience. Does anybody have questions? No? Thank you.
Thank you very much.
Yeah.